Alright guys, so we're going to do a sample problem, and I'm going to try to use this to convince you that energy is a really great concept and allows us to look at all the things we've been doing from a little bit of a different vantage point, but also makes it a lot easier. So we're going to do the same problem twice. It's an inclined plane problem, which is tough if you remember. And we're going to do it one time the conventional way, so the way that we've already learned using forces and vectors and all that, and then we're going to do it again using work, energy, potential energy, kinetic energy. So the question here, here's the problem. I have a 10 kilogram mass sitting on an inclined plane. It's 4 meters up a hill that's inclined at 30 degrees. I want to know what is its velocity at the bottom. So if we were going to get started over here, the first thing I would probably do is draw that little force diagram where gravity is pulling down, Fg, and we break that into a perpendicular and parallel force, F perpendicular, F parallel, and we say, well, this angle is the same as that angle, so it's 30 degrees, and the force I'm really concerned about is this one, the force pushing it down the hill. Parallel force is equal to Fg times the sine of theta, which in this case is 30 degrees. Now I know Fg, it's going to be, well, parallel equals the mass, which is 10. So 10 times negative 9.8, the acceleration of gravity, negative 9.8. And then the sine of 30 is 0.5. 0.5. So I have 10 times 9.8 is 98, times 0.5 is 49. So I have a parallel force of 49 newtons. Great. Well, what is that parallel force doing? It's pushing this block down the hill. So let me draw the picture again. I'm going to do what my Aunt Eileen does. I'm going to take the problem, just turn it sideways. So now I have a 10 kilogram block that's being pushed over 49 newtons, and it's going to do it for 4 meters. Well, I'm trying to find final velocity. If I know the force and the mass, I can find the acceleration, right? So F equals m times a. The mass is 10 kilograms. The force is 49 newtons. So the acceleration in this case will be a equals 4.9 meters per second squared. Okay, now I have the acceleration. And I know acceleration equals Vf minus Vo over t. But I don't know how long it's going to take to go 4 meters. Oh, but I can find that out. All I got to do is grab the workhorse formula. I'm going to run out of space. Let's go up here. The workhorse formula says delta x, so we'll call this delta x now, equals VOT plus 1/2 AT squared. And in this case, the VO is 0, so that goes away. So you get delta x equals 1/2 AT squared, which means 2 delta x over a, and the whole square root of that equals t. So delta x is 4, so that's 8, divided by 4.9. So I'm going to be somewhere around 16, a little bit higher than that. Square root of that is about 4 seconds, so time is about 4 seconds. Make sure I did that right. 8 divided by 5. Oh, I'm sorry. That doesn't make any sense. See? Calculators are good for calculations. I'm good for algebra. 2 times delta x is going to be 8. And 8 divided by 4.9 is about 1.6, not 16. So 1.6. So the square root of 1.6 is probably somewhere in about the 1.2 seconds, something like that. Well, that time goes down into here. VO was 0, and acceleration was 4.9. One more step, pull the calculator, we got a final answer. But look how much work it took just to figure out how fast it's going. Now, same exact problem, but we're going to use potential energy and kinetic energy instead. So let's draw a little border here because it's kind of encroached. Don't worry, this will be enough space. So 30-degree triangle, 4 meters up. So if I wanted, I could draw a vertical line here and say, well, if this is a right triangle, then this block is 2 meters off the ground. It's 2 meters above the ground. That's where it is. So this block right now has potential energy. It has the ability to push. It can roll down this ramp. And I can say exactly how much potential energy it has. I can say, well, U equals M times AG times height, which is easy to calculate. U equals, and I won't even do it right now, actually, because I want to show you that it gets even simpler. Well, where does that potential energy go to? When this block gets to the bottom of the ramp, it doesn't have any potential energy. You know, there's nothing about being in this position that says it has the ability to do work. It wouldn't start moving. It doesn't have the ability to push. But when it gets down here, it'll be moving. It'll have some velocity. So it will have kinetic energy. Well, where does that kinetic energy come from? It came from the potential energy. So we could say the energy is always equal to all the potential and all the kinetic. And the law of conservation of energy says that this can't change in a closed system. Since nothing's coming in or out of this problem, that's a constant number. At the top of this problem, there's no kinetic energy. It's not moving. At the bottom of this problem, there's no potential energy. It's on the ground. So that means all of the potential energy turned into kinetic energy, which means that U at the top equals KE at the bottom. And to remind ourselves, kinetic energy equals 1/2 mv squared. So now if we put this together, M times AG times H equals 1/2 mv squared. Masses cancel out. My V equals the square root of 2 AG H. That's it. Now, if we put numbers in here, 2 times AG, so that's about 20, times H, which is 2, so about 40. So square root of 40, that's putting us with the base somewhere around 7, a little less, like 6 point something. So 6 point something over here, somewhere in that ballpark. Well, remember, up here I'm getting a time of a little bit greater than 1, so call it 1.2. 1.2 times about 5 is giving me about 6. If you go through and use your calculator, you'll find out these numbers come out to be the same. Now, your choice, that formula or all of that. Now, that's for an inclined plane problem. Suppose instead of going on an inclined plane, I said you have a block that's on a roller coaster, and the roller coaster is all wiggly up and down. This problem's impossible to do with Newtonian physics. It's impossible to do it, unless you want to do a whole bunch of calculus. And we don't want to do that. We're lazy, but we're good lazy. We want good, simple solutions. And applying energy to these problems gives us good, simple solutions. So hopefully that makes sense, but we'll go over a little bit more. Bye now.